Dear students, in previous class we were discussing the continuity of a function. So, a function f is continuous at a particular point c. If x of all n is delta neighborhood of c, then f of x of all n epsilon neighborhood of f of c. F is continuous at a point c means if x of all n delta neighborhood of c, then f of x of all n, if x of all n delta neighborhood of c, v delta c, then f of x of all n the epsilon neighborhood of f of c. So this is the definition of continuity of a function. Also we stated that if f and g are any two functions which are continuous functions over same domain, then f plus g, f minus g, f into g, as well as when g differs from 0, f by g are continuous at that points. Also, function is continuous on a given set means the function is continuous at each and every point of that set. Okay. Also, we have stated that the polynomial function is a continuous function. What is a polynomial function? F of x equals a0 plus a1x plus a2x square plus etc. plus an x power n. F of x equals a0 plus a1x plus etc. plus an x power n. So this is a polynomial function. So polynomial function is continuous on, which is continuous on R. Polynomial function is continuous on R. Agreed. Now, what about the rational function? The rational function is also continuous on R. Why? The rational function means, suppose r of x be the rational function, r of x equals some px by q, p of x by q of x, where p of x and q of x are polynomial functions. P of x and q of x are polynomial functions. Also we know that the polynomial functions are continuous on R. Therefore both the p of x and q of x are continuous on R. But we know that when f and g are continuous, f by g is continuous. So here p of x by q of x is continuous provided q of x differs from 0. Then the rational function is also continuous on R. Agreed. So these are the preliminary results regarding the continuity of functions. Now what about a sine function? F of x equals sine x. Is it continuous? Sine function. F of x equals sine x. What about the continuity of this sine x? Sine function, is it continuous? So if you draw the graph of sine function in a certain interval, then you can see that the graph has no jump or no break. Then immediately conclude that the sine function is a continuous function. But how to prove theoretically? Geometrically it is immediate. How to prove theoretically? So for theoretically, we know that mod cos x. What is mod cos x? Mod cos x less than or equals mod cos x less than or equals 1. Agreed. So mod cos x means it is minus 1. That is minus 1 less than or equals cos x less than or equals 1. Agreed. If you integrate, what do you get? Integral minus 1 dx less than or equals integral cos x dx less than or equals integral 1 dx. Clear? Integral minus 1 dx means it is minus x less than or equals integral cos x means sin x less than or equals integral 1 dx, that is x. So that means modulus of sin x less than or equals x. So mod sin z less than or equals z. Mod sin x less than or equals x, as well as mod cos x less than or equals 1. Agreed. So to prove sin x is a continuous function, what about sin x minus sin c? Modulus of sin x minus sin c. modulus of sin x minus sin c. So it is of the form sin c minus sin d. What is sin c minus sin d? Sin c minus sin d is 2 sin c plus d by 2. That is 2 sin c plus, instead of c here x, 2 sin c plus d by 2 into sin c minus sin d into cos 2 sin c minus sin d, sin c minus sin d. It is 2 sin c minus d by 2, 2 sin c minus d by 2 into cos c plus d by 2. Agreed? So this is of the form sin x minus sin c, sin c minus sin d. What is sin c minus sin d? 2 cos c plus d by 2, sin c minus d by 2. Okay, so mod sin x minus sin c is nothing but modulus of 2 sin x minus c by 2 cos x plus c by 2. Agreed? So here which is less than or equals 2 into, why this less than or equals? Simply it equals 2 into modulus of sin x minus c by 2 into modulus of cos x plus c by 2. Clear? So which is less than or equals 2 into, what is mod sin x minus c by 2? Mod sin x less than or equals x. So mod sin x minus c by 2 is less than or equals, come on, modulus of x minus c by 2. Or it is x minus c by 2. So into mod cos x plus c by 2. Mod cos x less than or equals 1. So it is less than or equals 1. That means it equals modulus of x minus c. 2 and 2 are cancelling. So mod sin x minus sin c less than or equals modulus of x minus c. So what's our conclusion? Mod sin x minus sin c less than or equals modulus of x minus c means if x tends to c, sin x tends to sin c. Okay, mod sin x minus sin c less than or equals mod x minus c means if x tends to c or limit x tends to c, sin x equals sin c. So your conclusion is sin is a continuous function. Clear? So sine function is continuous. Now similarly, what about the cosine function? Is it continuous? For continuity of the cosine function, we consider instead of sin x minus sin c, you consider cos x minus cos c. What is cos c minus cos d? Cos c minus cos d is, yes, it is 2 sin c plus d by 2 sin c minus d by 2. Okay, so consider cos x minus or mod cos x minus cos c. Modulus of cos x minus cos c. It is equals to sin c plus d by 2 modulus of 2 sin c plus d by 2 means x plus c by 2 into sin x minus c by 2. Okay. So that is 2 sin x plus c by 2 sin x minus c by 2. So it is equals 2 into modulus of sin x plus c by 2 into sin x minus modulus of sin x minus c by 2. Okay. So, but mod sin such less than or equals such. So mod sin x minus c by 2 less than or equals modulus of x minus c. Since c is in arbitrary, so we have cos x tends to cos c if x tends to c. Okay. Therefore, the cosine function is also a continuous function. So sine function and cosine functions are continuous. Now also the polynomial function on set of R, polynomial function on reals is a continuous function, a rational function is also a continuous function, but we already see that the signum function is discontinuous. Signum function is discontinuous at the point x equals 0. Agree. Now, if f is continuous on R, f is continuous. F is continuous on R. What about a mod f? Or f is continuous on R or f is continuous at C? F is continuous at C. What about a mod f of? Mod f of? Is it continuous at C? Sure. When f is continuous at C, then modulus of f is also continuous at C. How to prove this one? F is continuous at C means modulus of f of x minus f of c strictly less than epsilon. Great. If x modulus of x minus c less than delta, then modulus of f of x minus f of c strictly less than epsilon. Agree. F is continuous at c means when mod x minus c less than delta, then modulus of f of x minus f of c strictly less than epsilon. But we know that. What about modulus of mod x minus mod y? Modulus of mod x minus mod y or modulus of mod a minus mod b less than or equals modulus of x minus y. Sure? Okay. So, to show mod f is continuous, consider mod f is continuous at C, consider modulus of f of x minus modulus of f of c. So to show, listen, to show mod f is continuous at C, it is enough to show that modulus of f of x minus mod f of c strictly less than some epsilon. According to this argument, this identity, modulus of mod x minus mod y less than or equals mod x minus y. Therefore, modulus of mod fx minus mod f of c less than or equals modulus of f of x minus f of c. But what is modulus of f of x minus f of c? It is strictly less than epsilon. Therefore, modulus of mod f of x minus mod f of c strictly less than epsilon provided modulus of x minus c less than delta. That means modulus of f mod f is also continuous at c. Okay. So, we can deduce a result from here. If f is continuous at a particular point, then its modulus function is also continuous at that point. Then, we also say that when f is continuous on a given set A, then mod f is continuous on the given set. Why? A set is continuous on, a function is continuous on a set means the function is continuous at each and every point of that set. So when f is continuous on A, f is continuous at each and every point on that set. According to this argument, mod f is continuous at each and every point of that set. Therefore, mod f is continuous on the given set. Clear? Okay. Now, we already proved that. So we are going. We already proved that if f and g are continuous, then f plus g, f minus g, f into g, f by g, etc. are continuous. Okay. Here, we prove that the composition of two continuous functions is also continuous. What is the composition of continuous function? Composition means, let us consider two functions, f from a to r. F from a to r and g from b to r, where a and b are any two non-empty subsets of R. A and b are non-empty subsets of R. F from a to r, g from b to r. Also, f of a is a part of b. With f of a is a part of b. Then to show that the composition, if f is continuous at C, moreover, if f is continuous at C, f is continuous at C. And G is continuous at B. What is this B? B equals f of C. Then the composition function, G composition f from A to R, G composition f from A to R is continuous at C. This is the another important result. That is, the composition of two continuous function is continuous. What is the composition? Means f from a to r, a to r, f from a to r, and g from b to r, g from b to r. B means this is what is f of a? F of a is a part of b. Therefore, this is the composition. G composition f is from a to. Okay, b is a part of. So, to prove this composition function, G composition f is continuous at the point where f is continuous. Here f is continuous at C, G is continuous at B, B means f of C. Then we have to show that G composition f from A to R is also continuous at the given point C. How? So here, its proof is, a function f is continuous. We know that f is continuous at C. F is continuous at C means, if x fall in the delta neighborhood of C, then f of x fall in epsilon neighborhood of f of C. So this is the definition of continuity of a function. Means x fall in v delta C means mod x minus c less than delta. F of x fall in v epsilon of f of c means mod f of x minus f of c strictly less than epsilon. That is the definition of continuity. So here, let epsilon is positive. Let epsilon being positive, and w be the epsilon neighborhood of g of b. W be the epsilon neighborhood of g of b. W be the epsilon neighborhood of g of b. Then, given g is continuous, what is g? It is the hypothesis g is continuous at b. What is actually b? b equals f of c. So g is continuous. G is continuous at b equals f of c. Okay, that means there exists a delta neighborhood. There exists a delta neighborhood v of b. By this argument, there exists a delta neighborhood v of b. B means, what is b? B is f of c. There exists a delta neighborhood of b, delta neighborhood v of b, such that, come on, according to this argument, if instead of x, let y. If y fall in v intersection b, then g of y fall in w. Okay, then g of y fall in w. X fall in b delta c, f of x fall in b epsilon f of c. That is, if f is continuous at a, then if x fall in b delta c intersection a, then f of x fall in b delta f c. Why? X is fall in b delta c, as well as this x is to sum from where? A itself. Therefore, x fall in b delta c intersection a. So according to that argument, if y fall in b intersection b, where v be the delta neighborhood of f of c, then g of y fall in w, w be the epsilon neighborhood of g of y. Okay? Right. So mark it as equation 1. Again, what is f? F is continuous at C. That's also given. F is continuous at C. Then there exists a gamma neighborhood u of C. There exists a gamma neighborhood u of C such that if x fall in x is from where? A, and x fall in also u, means x fall in u intersection A. If x fall in u intersection A, then f of x fall in where? Then f of x fall in v. Okay, f of x fall in v. But f of x fall in v, so you also say that f of x fall in v intersection b also. Why? See, f of a is a part of b. It is given. F of a is a part of b. When x fall in a and f is continuous, therefore f of x fall in f of a. So x fall in a, f of x fall in f of a. But what is f of a? F of a is a part of b. Therefore f of x fall in b. f of x fall in V as well as f of x fall in B, that means f of x fall in V intersection B. So therefore from this equation, if y fall in V intersection B, g of y fall in W, and if x fall in U intersection A, then f of x fall in V intersection B. So combines. Means therefore from equation 1 there exists a gamma neighborhood V of C such that if x fall in combines, if x fall in U intersection A, then g of f of x, here g of y, instead of y, here it is g of f of x fall in, where g of f of x fall in W. Okay, g of f of x fall in W. So g of f of x fall in W means, what is g of f of x? It is g composition f of x that fall in W. Since W is arbitrary, epsilon W is an arbitrary epsilon neighborhood of g of V, therefore g composition f is continuous vector C. So the result is important. When f is continuous at C, g is continuous at f of C, then their composition, g composition f is continuous. So that means the composition of two continuous functions is always continuous. So by using this identity or these arguments, we can solve some problems. So how? F of x equals, consider a problem. Consider f of x equals square root of x plus root x. Square root of x plus root x. How to check the continuity of this function? For x greater than or equals 0. How to check? So put a g of x equals, put a g of x equals root x, and f of x equals x plus root x. We know that root x is a continuous function. Okay, root x is continuous. X is polynomial, so x plus root x is also continuous. Clearly, g is continuous, f is continuous. Therefore, the composition is continuous. What is g composition f? So g composition f of x equals x plus root x. That is also continuous. So if two functions are continuous, then their composition is also continuous. Agreed. So the result is important. Then you can solve some problems by using these arguments like this. F of x equals root x plus square root of x plus root x. So g of x is root x, f of x equals x plus root x. We know that root x is continuous, x plus root x is also continuous. Then but g composition f of x is square root of x plus root x, hence it is also